In every machine that moves, everything from a screaming race car to a simple sewing machine, there's this hidden partnership at play. We're always focused on the go, right? The acceleration, the power. But what if I told you the real secret, the key to making things truly efficient and controlled, lies in the stop? Today, we're going to explore this unseen engine.
Sounds like a bit of a stretch, doesn't it? A Formula One car and your smartwatch. What could they possibly have in common? Well, believe it or not, they share a fundamental engineering secret. It's a principle that is totally reshaping how we think about energy, and the answer is all about capturing something that we normally just throw away.
Okay, so at its core, any machine is really just a balancing act between two systems. You've got the drive system, the engine, the motor. That's the part that says go. It creates all the motion. And then you have the braking system, the part that says stop, which is all about controlling that motion. For literally centuries, we've seen these as opposing forces. Go was productive, and stop was, well, it was just stopping. But that's all starting to change.
To really see this shift in action, we have to go to one of the most demanding places on the entire planet, a place where every single millisecond and every drop of energy is critical. We're talking about the magic of KERS, the Kinetic Energy Recovery System.
That's right. This whole idea was born on the racetrack. In Formula One, you have a car going at insane speeds, and it has to slow down for a corner, like incredibly fast. Engineers looked at that and saw all this energy from slowing down just being wasted, literally turned into useless heat. So they asked a really simple but brilliant question. What if we could actually capture that energy and use it?
So what is this energy they were trying to grab? It's called kinetic energy, and it's pretty simple, really. It's the energy an object has just because it's moving. The faster something is, the heavier it is, the more kinetic energy it has. So, when you slam on the brakes in your car, you're getting rid of all that energy. But the real question is, where does it go?
And this is where KERS comes in. It's a beautiful four-step solution. First, the car brakes, but instead of just turning all that kinetic energy into wasted heat, the system captures it. Then it stores that energy, usually in a super advanced battery or a crazy fast spinning flywheel. And then, this is the cool part, the driver can hit a button for a boost, deploying that captured energy for a sudden burst of acceleration. It is literally turning the act of stopping into a tool to go faster.
But to really truly appreciate how clever this system is, we need to dig into the fundamental problem with stopping. Because in almost every machine you can possibly think of, braking means one thing. You're generating an absolutely incredible amount of wasted heat.
And look, this isn't just a theory, it's physics. This quote is from a General Motors patent from way back in 1969. They laid it out perfectly. To slow a car down, the kinetic energy of that whole moving vehicle has to be converted into heat. There's just no way around it. And we're not talking about a little bit of warmth here.
Nope, we are talking about temperatures that can easily hit over 1,000 degrees Fahrenheit on the surface of a brake disc. That is hot enough to make solid steel glow red. At those kinds of temperatures, brakes can suffer from something called brake fade, where the material literally loses its ability to create friction. Your brakes just stop working. So managing this heat isn't just about being efficient, it's about surviving.
You know, what's really fascinating about that old patent is the solution it came up with for all that heat. It describes using a heat pipe. It sounds complex, but it's a deceptively simple device. Basically, it uses a liquid that boils at the hot end, right at the brake, and it travels as a gas to a cooler end, where it turns back into a liquid and releases its heat. It's like a superhighway for heat, just whisking it away from the parts that matter, with unbelievable efficiency. So, we have these really clever solutions, like heat pipes, to manage the consequences of stopping. But all of this starts to reveal a much bigger picture, right? It's about the fundamental choices and the trade-offs that engineers have to make for both stopping and going. And this tension, it exists absolutely everywhere, not just in Formula One cars.
Let's start with the Go system, the motor itself. It's never just about raw power. The type of motor you choose creates this whole cascade of trade-offs that affects everything from how the machine feels to use to how reliable it is in the long run.
To see exactly what I mean, let's look at a totally unexpected example: industrial sewing machines. This table, which is based on actual discussions between people who use these things every day, shows the trade-offs perfectly. Take response time. A direct drive motor is lightning fast. It gives the operator incredible stitch-by-stitch precision. But when it comes to maintenance and repair, the simple old belt drive is king. It's cheap, it's easy to fix. The direct drive, that's often a specialized part that can cost a fortune to replace. It's a classic engineering dilemma. Do you want peak performance or do you want practicality?
Okay, so that's the go side of the equation. What about the stop side? Well, not surprisingly, we find the exact same pattern of give and take. Choosing a braking system means you're constantly balancing these competing priorities against each other.
And here, we can see that in action, comparing two common types of industrial brakes, hydraulic or pneumatic brakes. They can generate immense stopping power, and they're fantastic at getting rid of heat, perfect for heavy-duty, repetitive jobs. But they can be a bit slower to react. On the other hand, electromagnetic brakes are unbelievably fast and precise, but they don't handle heat nearly as well, and they just don't have that same brute force stopping power. So the question becomes, what do you need more? Power and endurance, or speed and precision?
And this all brings us to a really fascinating place. We've looked at go systems and stop systems as this series of trade-offs. But what if this stop system could actually help the go system? This diagram shows a concept for a sewing machine where the braking momentum actually turns a tiny generator. It's regenerative braking, the exact same principle we saw in the Formula One car, just apply it on a completely different scale. Mind-blowing, right?
This whole idea that stopping can help us go isn't just for race cars or industrial machines. This is a principle that's being scaled way, way down, and it could very soon be powering the technology we carry with us every single day.
And just like that, we've come full circle. The very same high-concept KERS technology from Formula One is being totally reimagined and miniaturized. The goal now is to build it into things like smartwatches, fitness trackers, and all kinds of other wearable devices.
The potential here is just staggering. Research is showing that these tiny little KERS systems could recover up to 70% of the kinetic energy from your own body's movement, just walking, swinging your arms, you name it. That energy, which right now is completely wasted, could be used to extend your device's battery life, or maybe, just maybe, get rid of the need to charge it at all.
Now, of course, we're not quite there yet. There are some huge engineering hurdles to get over. I mean, making these systems tiny without losing all their efficiency, that's tough. They have to be durable enough to survive daily life, safe enough to wear, and cheap enough to actually put in a product you can buy. But here's the thing. Engineers are actively working on solving every single one of these problems right now.
So let's go all the way back to that hidden link between the race car and the smartwatch. It's the simple, powerful idea that energy is just too valuable to waste. That the simple act of stopping, of slowing down, actually holds the potential to power our future. It leaves you with one final thought. What if a simple act of living your life, of just moving through your day, could generate all the power you'll ever need?